All right, so I have sort of an overview talk of how we now get a fully functioning node, wireless sensor node, out of the various technologies that we've used or been researching throughout the lab. So there's a lot of names on the slide. I don't think I need to go through them. Paul's covered most of the researchers and PIs. So here's our vision of the future, sort of, is a very small wireless sensor node with our various integrated research projects that individually have been shown to work quite well over the years. And now, in this talk, I'm trying to show that we can connect these all together to get a functioning node. The biggest problem going forward, or to achieve that, was basically the energy harvesting component. So this is one of my devices. Here's Lindsay's devices. So we know that each one of these individual components works. The radios you can buy commercially. You can get commercial sensors. Richard just showed us that a variety of his sensors work. And then you can either get off-the-shelf energy storage, or Rich will show you that you can print energy storage. So it's really just, can we provide enough power to get all these systems working together? And so as a review, about a year ago, we showed you that we installed some of our energy harvesters on large industrial motors in this building. There's 15 and 30 kilowatt motors running a variety of systems to back up the Marvell Nano Lab and also to run the air conditioning, chillers, and everything in this building. And so, and I should take a step back. And so these commercial radios that Richard's talked about briefly, you need sort of 100 microwatts to get things going. And the radio is by far the most power-hungry component of this whole system. So if we can get 100 microwatts time average power out of one of these energy harvesters, then we can potentially get something going. And so we showed that in these real-world deployments, you can get hundreds of microwatts to even milliwatts from the normal operation of these pumps. The biggest challenge we then had was, well, can we turn this power? We were basically just making heaters because we were dumping this energy across a resistor to determine the power. Can we now rectify this into something useful by electronics? And the biggest challenge was that the voltage coming out of these devices was quite low. Ultimately, you'd like to see several volts to make this easily rectifiable and stored on a capacitor or battery. So then 6 months ago, we redesigned the magnetic circuit in these devices. And we've gotten sort of an order of magnitude improvement in the voltage output. So we transformed it by increasing the magnetic field that the coils see, and then also making some better coils. And now we're seeing sort of 2 to 4 volts at operation levels that you would normally see with these large industrial motors. And so then 6 months ago, we also began rectifying these signals that we're seeing. So we did the simplest rectification scheme that you could possibly have, which is just a diode bridge, stored it on a large capacitor, and then hooked it up to one of these Texas Instrument motes that Richard briefly touched on. So we initially just used the shaker table over in Echeverry Hall to simulate the vibrations and put together this simple demo that's basically using the onboard temperature sensor of the Texas Instrument mote. And so we have a base station, and that's plotting temperature here. And then this is the temperature associated with our transmit node, which is being powered by our energy harvester and rectified signals. And so recently, we've now shown that this will work. Well, we've taken it from the shaker table to the pump room downstairs and shown that the normal operation of this pump here, which is a 15 kilowatt pump running chilled process water for the nanolab. Here's the acceleration spectrum associated with it operating, and this is the peak that we harvested. Open circuit, you can get 7 volts, so we're somewhere between 500 and microwatts and a milliwatt of power. And here's our sort of rectification power circuitry. You can see there's no batteries in the mote. You might be able to tell that there's an LED flashing as the base station node is receiving a signal. And ultimately, so now the biggest challenge we have is that we can get this demo working, but our power electronics is the biggest shortcoming now of the system. So we're only recovering something like 15% of the energy that the energy harvester is actually producing. And there's huge losses associated with the diode bridge and energy storage. And I guess, lastly, I have a video of this working. So the whole point is now we can integrate these disparate parts, connect them together. Even though it's not very pretty yet, we can get a fully functioning node. It's just sort of academic at this point to now take these large circuit boards and turn them into 3 or 4 boards and sensors on this size scale, and start deploying them on these pump motors. And replacing what we have now is wired monitoring nodes, which are monitoring the acceleration of these various pumps, and replace these over the next couple months with wireless nodes. So let's see if the video works. No. All right. So here's our harvester. We've jumpered it over to this. I apologize for the video. We've jumpered it over to the power conditioning. You could see LEDs flashing. And now these are the plots of the various temperatures associated with the base station node and the transmit node here. And eventually, I have cold hands, you'll see, but Fred, who has helped me put this all together, has much warmer hands apparently, and you'll see a jump in the signal in a moment. Yeah, this is my cold hands. There we go. And the video also shows that there's no sort of excessive vibration that we're taking advantage of. That's just the pump normally operating.